Welcome, everyone. Pleased to have you here with us for what I believe is our 80th episode of This is CDR. This is CDR is an online event series presented by OpenAir to explore the range of carbon removal solutions currently being researched, developed, and deployed, and to contextualize them for policy. OpenAir works on CDR policy pretty much at every level of government here in the US, as well as at national and subnational jurisdictions globally. My name is Toby Bryce. I'm based in Brooklyn, New York, and work on CDR policy and market development with OpenAir. If you haven't done so already, please say hello in the chat, introduce yourself, and tell us where you're tuning in from, and make sure you direct that message to everyone and not just host and panelists so everyone can hear from you. Quick background on OpenAir. If you're not familiar with us, we're an all-volunteer network dedicated to advancing the equitable and responsible deployment of carbon removal. We are a global community. We work together on shared open source projects that we call missions in the areas of policy, innovation, communications, and activist market development. Here is a link to the missions or a picture of the missions page on our website. Our co-founder, Chris Neidl, is running the chat, and he'll put some links in there so that you can find our website, see what the missions are, and there will be a link as well that you can fill out to join our group. And that means hopping onto a Discord server, which is how we manage our projects and communicate with each other. So please take a look at that and consider it. Two really important, actually one quick thing. So before we get started, we always like to define our terms. This is a definition of carbon removal from a great resource called the CDR Primer, and we'll put a link to that in the chat. It's an online textbook that's also a physical textbook that really is a great, it's put together by 50 plus leading CDR experts, and it's a great way to learn about carbon removal. And the definition is purposeful human activity to remove CO2 from the atmosphere and durably store it in geological, terrestrial, or ocean reservoirs or in long-lived products. So it's an atmospheric function. It's removing CO2 from the atmosphere, and it's a range of technologies and approaches and methods that can do that. This is also essentially the same definition that the IPCC uses, so it's one that we think is a good one to work with. Really important whenever we talk about carbon removal, and we say it every show, carbon removal, it's important, it's essential to addressing the climate crisis, but it is in no way, shape, or form any sort of substitute for reducing emissions and decarbonizing the global economy as completely and as quickly as possible, full stop. If we don't reduce emissions and decarbonize the economy, carbon removal is designed to get us the last 10% to our climate goal, but without the 90% work of reducing emissions and decarbonization, we're not going to end up in a good place. So we need to work on both, and we need to make sure that we do not use carbon removal as any sort of excuse for not reducing emissions as quickly and as completely as possible. Two emissions that we're working on that we just want to highlight. If you happen to be in California or Massachusetts, we're working on two really important CDR state level policies in those states. That's actually the wrong bill number for the Massachusetts one, but Chris will put a link in the chat to information about both bills, and also a really simple call tool that you can use if you are in those states to contact your local representatives. You can really use the help, and would be super great if you do live in those states, if you could get in touch with us and get involved in our advocacy efforts for the bill. I'm going to hand it over to my colleague Megha Raghavan, and she is going to introduce herself and talk a little bit about run of show, and then introduce today's presenters.
Hello, hi, I'm Megha Raghavan. I am an OpenAir member based in London, and I work on policy and market development as well. So yeah, just on the format, we'll start with a quick presentation, followed by a few prepared questions, and then moderated audience Q&A. So if you have any questions as we go along, just put them into the Q&A box. It is separate from the chat box, so make sure you find the right one, which just helps us to organize the questions a little bit better. We will also be recording the event, so we'll send the recording out to all of you who registered, and we'll post it to OpenAir's website and to our YouTube channel. All right, this week we're very pleased to welcome Crew Carbon founder and CEO Joachim Katchinoff and lead process engineer Kevin Vu to discuss how the company is moving carbon from the fast to the slow cycle using enhanced weathering and engineered systems for permanent, low-cost, and measurable carbon dioxide removal. Crew has been selected as one of the Frontier Climate's early carbon removal pre-purchase companies and has received grant support from the Carbon to Sea initiative. Joachim co-founded Crew in 2022, and prior to that, he worked for 7 years as a geochemist investigating fundamental questions about the carbon cycle, weathering dynamics, and biogeochemical cycles. Joachim holds a Ph.D. from Yale University in Earth and Planetary Sciences as of 2022, and a Bachelor of Science in Geology from the College of William and Mary. Kevin Vu is a process engineer specializing in water and wastewater treatment. He has years of experience in R&D engineering, pilot deployments, practical design of municipal and industrial treatment systems, and modeling of biological process units and sewage networks. He holds a BE in civil engineering and an MS in environmental science and engineering from Caltech, where he conducted applied research on electrochemical processes for decentralized water treatment funded by the Bill and Melinda Gates Foundation. So whenever you guys are ready, feel free to come on and get started.
Amazing, thanks. Pull up the slides now. Great. Thanks, team, for the nice introduction. I just want to start off by thanking the rest of the OpenAir team for really giving us the time and the platform. I think This is CDR series is really an amazing opportunity to highlight and support all the amazing efforts in the space. So huge thanks again for facilitating this. We're really excited to delve in and tell you a little bit more about Crew and what we've been building. So although this audience is well-versed with carbon removal, I want to start off and really highlight that at Crew, what we're doing is taking advantage of the well-established weathering reactions for carbon dioxide removal. As a geochemist who's spent his last 8 years studying this process, it's an interesting one, and it's interesting to me how most folks in the world don't realize that the reason Earth has been habitable for almost 4 billion years is through rocks removing carbon. And really how it works is that CO2 will naturally equilibrate with fluids at Earth's surface, like rainwater or river water, to form carbonic acid. And when that carbonic acid interacts with silicate and carbonate rocks, it goes through a chemical reaction which dissolves the rock, converting that CO2 into a trapped, more stable form of carbon called the bicarbonate ion. And eventually, this bicarbonate ion will make its way to the world's oceans, where it will be trapped for many thousands of years, leading to permanent carbon dioxide removal. So today, it's a process that removes around 1 billion tons of CO2 per year. But as I just highlighted, it's a slow process. It operates on geological timescales. And so the whole premise behind enhanced weathering is to accelerate that process with 2 major steps. The first one is grinding naturally occurring rock to increase its reactive surface area. And then secondly, putting that crushed rock feedstock in environments where it can more readily react with water and carbon dioxide. So conventional enhanced weathering, which looks to deploy these feedstock in agricultural soils or maybe directly to the ocean, has a lot of promise and a lot of scale. And there's been a lot of amazing work that's been done to date to prove this process out. But it also has its challenges. For example, there are MRV risks. Making measurements on how much carbon you can remove when engaging in background weathering reactions and trying to leverage this process in diffuse open settings becomes difficult. There is some uncertainty with how much carbon you can measurably remove. There's also environmental constraints like complex soil conditions that can have various effects on the efficiency of enhanced weathering, for example, soil moisture. And finally, there may be acceptance and permitting risks, specifically for things like ocean-based enhanced weathering, or maybe the use of specific minerals that have potential metals that could end up getting into our soil. So specifically, what we do at Crew is use engineered enhanced weathering to remove carbon dioxide really at the nexus of climate tech and wastewater. And it's really by combining a nature-based solution with engineered processes that we can start to mitigate many of the risks and challenges associated with conventional enhanced rock weathering. So you might be asking yourself, why wastewater? I'm not sure how many folks in the audience today have been to a wastewater treatment facility, but if you have the opportunity to, I would really encourage you. These facilities are some of the most amazing pieces of human ingenuity and engineering, and it's just really amazing infrastructure that has gone in place to treat our wastewater. So as an overview, every single year, huge amounts of wastewater is produced. I'll say a number here that is so big, it's hard to even visualize, but every year around 1 × 10 to the 15th liters of wastewater are produced annually. Again, big number, hard to visualize, but as a point of comparison, that's about 3 to 5% of the total river water flux. That's a massive amount of water. 3 to 5% doesn't sound like that much, but when you're thinking about that's comparison to every single drop in the hydrological cycle. And we produce that in terms of wastewater. So this water and waste is oftentimes channelized, taken to discrete locations for removal of pollutants in that wastewater, including pollutants like carbon. And the whole goal is to remove those pollutants before that clean water can be discharged back into the environment. Wastewater treatment aims to remove these pollutants like carbon at more than 95% efficiency so that water is safe to discharge. And oftentimes that water is discharged directly to large river systems or oftentimes directly to the ocean. And really what the heavy lifting of wastewater treatment is, you might ask yourself, what is actual wastewater treatment? It's really done by trillions of microbes in bioreactor tanks like the one I'm showing on the slide right now, where in simple terms, wastewater treatment is leveraging its own nature-based solution for rapid microbial action to remove these pollutants. Now, if you put on your carbon cycle lenses, we can go through exactly how CO2 fits into this wastewater treatment process. So starting in the top left, we start with CO2 in the atmosphere, which is efficiently fixed by biomass that can either be used as by us as food or in various industrial products. That biomass is then consumed or utilized and then discharged as solid carbonaceous waste to the wastewater treatment facility. And what happens in the wastewater treatment process is that these massive bioreactors that are already in place have trillions of microbes that rapidly convert solid carbon into carbon dioxide and produce a wide range of other greenhouse gases. Under business as usual, this biogenic release of carbon releases back to the atmosphere either during the treatment process itself or downstream post-discharge. And it's really this carbon, this elevated source of CO2 that we're targeting as part of CREW. So if we step into the actual wastewater facility, we can see how that CO2 is being produced. And I can tell you it's being produced at a really high concentration as part of this fast biological cycle, this fast bioreactor process that's happening on steroids. So when we make measurements of the direct biogenic CO2 that is being produced during the biological treatment process, we can see it's occurring at highly concentrated and rapid rates. In the surface area, which is kind of equivalent to that of a bath towel, CO2 is being emitted between 1 and up to 10 kilograms of CO2 every single day at these wastewater facilities. And that is really the equivalent of several orders of magnitude higher CO2 than you can find in the atmosphere, which I think really, really underpins just how unique of an environment wastewater treatment really is. And so our goal at CREW is to take advantage of this. We want to shuttle this carbon from the fast biological cycle through enhanced weathering reactions to have permanent removal of this carbon as this dissolved trapped carbon ion. Once trapped through our process, that carbon will continue through the treatment process and then eventually be discharged with the rest of the effluent either directly to large rivers or the oceans for long-term storage. So it's an amazing environment where we can take advantage of all this carbon, quickly shuttle it into a form through these weathering reactions and discharge those weathering products directly to the place where it needs to be stored for many thousands of years. And so you can kind of think of this as another form of bikers or BECCS. We're taking advantage of biology to fix and create carbon dioxide, and then we look to store it. So to really specify what CREW does is that we leverage enhanced weathering hardware and software that we've developed that uses either containerized reactors or integrated in directly existing infrastructure. And with this process, we do three things. One, we contact CO2-rich fluids with carbon-negative minerals in controlled environments like wastewater treatment facilities. We then deploy the sensor arrays that we've developed at the front end and at the back end of these systems to measure the real-time chemistry and to quantify how much CO2 we can remove. We can measure the fluids coming in and coming out, and that allows us for a more straightforward mass balance of the carbon system. And then critically, the last step is that because we're dealing with in situ sensors and engineered systems, we can optimize system operation to most efficiently remove carbon dioxide. And finally, because we're generating these highly durable carbon credits, we can then sell those credits to other businesses or on marketplaces. We're currently partnering with the Frontier Fund to sell our credits to them initially. On top of this, our process also has the benefit of co-benefits, something that we can get into in the next couple slides and that Kevin will highlight. So again, we're zooming in even further into the actual wastewater treatment process. And these are really the chemical processes that are occurring so that everyone's on the same page here. CO2, if we're starting on the top left, CO2 is being produced from the decomposition of organic matter in the wastewater. And that CO2 combines with water to form carbonic acid. As such, typically what happens during biological treatment is the pH of the wastewater decreases as you're forming this carbonic acid and as you're forming other organic acids. By integrating our enhanced weathering process here, we can react that carbonic acid that's being produced by the rapidly acting microbes with these naturally occurring rocks and minerals to trap that CO2 as dissolved bicarbonate. And it's really through this pH shift that's happening in this aqueous system where we're able to rapidly remove this CO2. At the same time, because we're effectively adjusting the wastewater pH, there are positive knock-on effects to our process. Many of the microbes that are responsible for the heavy lifting for that biological treatment of the wastewater are highly affected by pH. They don't like acidic conditions. And so by removing this acidity, we can actually make those microbes do their jobs more effectively. So talking you through kind of the major steps of what a crew deployment looks like, there are four major parts of it. So first, we install a system that can handle and source feedstock from the surrounding area. Our whole goal is to be able to, one, identify the most affordable feedstocks, and two, identify the feedstocks that will react as rapidly as possible with as little impact as possible. The next step is once we're able to source that feedstock on site, we then use our hardware and software to basically dose in the precise amount of rock either directly into the wastewater infrastructure themselves, into the bioreactors that are already there, or into containers that we've built ourselves. And really that dosing is based off of an understanding of the geochemistry as well as the engineering of the system. The third step is then we use the sensors that are in place to quantify real-time chemistry and help us identify how much carbon we are actually able to remove and control the rest of the system based off the live feedback that we can measure. And then finally, we've permanently stored this CO2 that's being produced as a stable form of carbon in the effluent flow while also providing additional co-benefits that Kevin can get into next.
So Joe has talked a lot about how crew approaches CDR, but let's turn our attention to the wastewater facilities themselves. Aside from their own climate goals, why would they choose a process like crew? Having worked with utilities and operators as an engineer, I can say that there are a few key priorities from their perspective, right? And at the top of their mind is meeting permit compliance for discharge. This includes pH and nutrients like nitrogen and phosphorus. Some facilities are already using expensive and carbon positive methods to adjusting pH, such as sodium hydroxide or quicklime. Our feedstock is cheaper, less hazardous alternative. And because of the carbon negative nature of our feedstock, we can remove and store carbon in a way that will also shift pH to a more appropriate levels in line with typical permits without fear of violating them. This leads to another priority, which is to keep the microbes happy, or bugs, as they call them in the industry. By capturing carbon, by removing the acidity in the form of carbonic acid, we can provide bugs with a more productive environment. And as Joe mentioned, these more productive bugs are essential to efficient nutrient removal, such as nitrification, where there can be a reduction in nitrous oxide emissions. And so for the customers and climate overall, our system is deployed in these engineered facilities where monitoring wastewater quality is necessary for day-to-day operations. Installing our MRV technology in these highly engineered facilities allows us to generate durable and fungible carbon credits. With relatively low capex, our goal is to sell credits for under $100 per ton at scale. And because wastewater facilities can be permitted to discharge into large bodies of natural waters, the endpoint for storage of carbon is clear and straightforward. Coupling this with permanent carbon storage with our MRV system means that we can achieve quantifiable impacts on larger climate goals. So these are some of the core co-benefits for our stakeholders, but I want to also take a step back and talk about wastewater in a wider context, right? This is a little bit of a busy slide, but I think it helps illustrate how wastewater is really central to daily life. So let's focus in on the shaded areas. The red shaded area in the U shape highlights infrastructure supporting human life, such as residents in rural or urban areas, right? And industrial facilities like chemical, electrical, and food that are all necessary for human progress, but as they also produce waste as a consequence. Ideally, this waste goes into the blue box in the middle of the figure, which represents some of the traditional treatment steps in a centralized wastewater facility. The goal is to take this waste from surrounding infrastructure and treat it for safe discharge into the green shaded area on the right, which represents rivers, oceans, etc. So from this, we can kind of see that wastewater is a major nexus, right? Some people like to say the water energy nexus that connects the built environment to the natural environment. But beyond CDR, there are additional opportunities for climate impact in wastewater facilities. So in the next slide, we can zoom in on the infrastructure related to wastewater. And so, there's a lot going on here, but again, let's focus on the little floating clouds, right? So you can see that there's not just CO2 emitted, but large quantities of nitrous oxide and methane in various pathways. 3 to 5% of total anthropogenic greenhouse gases are emitted globally. And if we can attack that, that's a significant amount of impact on climate. And we're starting to think now that wastewater is no longer just waste, right? Or a source of pollution. It's really a highly concentrated source of value. And so there are efforts to realize, for example, methane as biogas for energy production, metal recovery, and biosolids from nutrients as fertilizers. But from recent studies, we're also starting to better understand the emissions from these wastewater facilities. And it turns out we may be underestimating the greenhouse gases released from these facilities. There's opportunities to better learn and understand these emissions and better measure them. And that leads to how to improve or redesign a facility that works in concert with the environment. So for example, a wastewater facility in the UK is going to be built ground up and is designed to be carbon neutral using modern technologies and best practices. And the final point I want to leave you all with is that this is an industry, wastewater, that is necessary and has existed for as long as we've been generating waste, right? So when we're thinking about the uncertainty in carbon markets, existing infrastructure like wastewater is a great way to hedge against uncertainty by tying into processes that are going to be ever present. So with that, I'm going to pass it back to Joe to close this off.
Cool. Thanks, Kevin. Yeah, so just wrapping up in these last couple slides, wanted to highlight who the crew team is and what we're building and where we're going next. So as you can see here, with all these lovely people, the crew team is still relatively small, but we are actively growing. We're 5 full-time folks at the moment and up to 12, including the part-time team members like interns, consultants, contractors. We come from a wide range of academic and industrial backgrounds and are all driven by the carbon removal mission. We are also supported by a growing group of collaborators and supporting institutions and are really lucky to have them on board. Obviously open as always for any sort of future collaborations, so please do reach out. And finally, we have an amazing customer through the Frontier Fund. So we've really benefited from the support and advice from the good folks at Stripe and Shopify. So what does the future of Crew look like? What we're aiming through 2023 is really grow our first couple deployments to really increase our tractable climate impact as we laid out to you guys throughout this presentation. The goal is to allow us to deliver more and more carbon dioxide removal and deliver those credits to our initial partners at Frontier. For 2024, we're aiming to be deployed at 2 to 4 additional facilities. That is both municipal and industrial. And really, our goal and what we're targeting is by the middle of 2024, we want to be capturing CO2 at 1,000 tons per year, if not more. And with these plans, it will really allow us to be at the capacity to capture more than 30,000 tons of CO2 per year at the start of 2025. That really is our goal, and we think it's achievable by targeting this process. Really, if I can leave you with anything, our overarching vision is to use this nature-based solution in engineered systems for measurable and durable CO2 removal. And our vision is to really transform wastewater from this perceived source of pollution into a source of value, specifically through positive climate impact. So with that, I want to thank you all again for the time and for the opportunity, and really happy to get into any questions you may have. Thanks all.
That was great. Thank you guys so much. And really, I think in the beginning too, there was a really excellent explanation of the enhanced weathering process. And so we've seen a couple of enhanced weathering folks come on, and it was super helpful to see it laid out the way you did. So thank you. Just to get started, can you just to tell us about how you got interested in carbon removal and how the company formed? We've had a couple of your Yale colleagues on, Sinead Crotty from Yale Carbon Containment Lab and Dr. Planofsky.
Yeah.
Tell us about how this got started.
Yeah, absolutely. So just from my perspective, I did my undergrad in geology, and that was really driven by a couple different things. Always loved being in the outdoors. Growing up in Virginia, did a lot of things outside, fishing, even hunting at times, and just really enjoyed that experience. So that led me to geology. If I could understand the natural world and how it works, why are we alive? How is CO2 being controlled on Earth? Those were kind of the questions that led me to that. And eventually, decided to continue through master's, Ph.D, and other academic work to think about the global carbon cycle. It was, becoming very, very apparent at the start of my Ph.D. That we needed to make an impact, and we need to make an impact today. And it turns out the thing that I was studying, these weathering reactions that are responsible for CO2 removal, are, can be leveraged today for actual impact. And so it was through the obvious data that was showing that we needed to do something, that motivated me to use that academic background to do something more applied. And I was lucky to find a really motivated group of people at Yale who were thinking about how to leverage carbon dioxide, various pathways for carbon dioxide removal. And that's some amazing researchers at the Earth and Planetary Sciences Department, the Yale Carbon Containment Lab, also the YCNCC, the Yale Center for Natural Carbon Capture. That's a mouthful. And so basically, through a collaboration with various folks at Yale's, we really got behind the idea of CREW, thinking about how could we use enhanced weathering reactions beyond just the sort of conventional means, but are there any sort of novel ways that we could leverage this process to make impact beyond just applying it in agricultural fields? So that's really how it started. And it was, many years of research and development at Yale that allowed us to get to where we are today.
There really is a lot going on at Yale in terms of, ideation and company formation relating to carbon removal. It's super exciting to watch. And as we just discussed, the pizza. Kevin, you want to tell us a little bit about how you came to this?
Yeah, that's a bit of a long story. I mean, I guess to make it short, obviously I'm a water and wastewater engineer. My interest is originally in that. But through my work at grad school, I learned a lot about the contemporary issues of wastewater, and how we can better treat our waste for resource recovery, right, or to lower emissions. So after going into practice for a couple of years, I was really looking for an opportunity to kind of merge the two, right, both wastewater and climate. And I connected with Joe, and we really hit it off from there. So it just made a really good fit.
Awesome. So I was going to ask you guys about the form factor for your reactor, having read your Frontier app, which we put a link in the chat, which is probably more information than you would like to share, but it's out there. But maybe the form factor as a wastewater treatment plant is a better way to think of it. If you're going to be applying your your minerals to the existing process. Is that correct? Should we talk about that?
Yeah, happy to. I'll give a first pass, and then I'll throw it over to Kevin for
Let me throw out a couple things because I was Googling during your presentation. It looks like there are 16,000 wastewater treatment plants in the US and 110,000 globally. I'm sure there are multiple estimates, but there are a lot.
Yeah.
They're everywhere. And so it's a really interesting and kind of point of scale. And like, as you answer the question, maybe talk about obviously they range in size, but what is the average form factor of a wastewater treatment plant? And then how do you integrate with that? And what are the inputs, the outputs, the byproducts? Would love to hear a little bit of those numbers so we can understand a little better, like how the process can work.
Totally. Yeah. Like I said, I'll do a first pass and then throw it over to Kevin for any extra details. So generally, there's multiple ways to treat wastewater that have been developed over the years. If you look at the history of wastewater, it's actually although there's been sort of normal approaches to how to treat wastewater, the more modern version of wastewater treatment has only emerged in the last 50 years, 50, 60 years, which is a pretty incredible thing. But generally how wastewater happens is kind of through three major steps, and it's primary treatment, secondary treatment, and tertiary treatment. Some facilities have all three, some of them skip certain aspects, but generally that's the approach. Primary is basically where the wastewater comes in, and the whole goal is to sort of settle out the big chunks, like the twigs, the rocks, the bottles that make its way into the sewage system. So that's physical settling through dealing with the water itself, and then also screening. And then the second step, which is biological treatment, and this is really where a lot of the heavy lifting of wastewater treatment actually occurs, is the biological treatment step. These are those bioreactors that we highlighted. And it's funny, there's a lot of folks who are interested in the CDR space thinking about how can we rapidly produce CO2 in a way, or capture CO2 in a way. That process already happens in these bioreactors. These little bugs are, working very, very well to convert that solid carbonaceous wastewater into CO2. And not only are they attacking the carbon, they're attacking other pollutants, both biochemically removing them, but also physically through things like flocking. So most of the wastewater treatment happens in the biological treatment step. And then the final step is the tertiary, oftentimes disinfection. And so there's various ways you can try to disinfect your wastewater. A lot of folks will use things like bleach to kill off any of the microbes before it's eventually discharged back to the environment. And so you highlighted, there's a bunch of different plants. There's municipal facilities. There's also industrial facilities. They all come in various shapes and sizes. And so the form factor of an actual plant can change quite a bit, right? Some of the largest ones are treating billions of gallons of wastewater every single day. I will just stop there for a second to just highlight that's billions with a B. That is a just huge amount of wastewater every single day that is coming into this facility, treated, and then discharged within that same day. So that just kind of, again, highlights the engineering that goes into it, but all the amazing biogeochemistry that is leveraged to clean that water. And there's some really amazing innovation that's come up with that. So it can vary in size. One of the facilities that we've been looking at has a bioreactor tank itself is about 200 meters. It's a concrete tank, 200 meters long, about 100 meters wide. And that treats tens of millions of gallons of wastewater every single day, to give you a context. And so what we're trying to do is essentially tie into that existing infrastructure. And it's not a completely novel thing. Wastewater, as Kevin mentioned during the presentation, wastewater facilities oftentimes will try to adjust the pH of the wastewater themselves, right? They can either do that through changing the operational components of the treatment process, or they might add chemicals, alkaline chemicals to adjust the pH. So they will use things like quicklime or sodium hydroxide or magnesium hydroxide for that pH adjustment. So they already have that infrastructure in place, similar to ag enhanced weathering, where folks will already, spread material to adjust the soil pH. Wastewater facilities will oftentimes do the same. So we're basically a like for like replacement for those existing processes. So it's not terribly new to them that we would have dosing tanks, we would have sensors, and that we have materials coming in and out. They already do that every single day. And so it's easy for us to integrate with as little touch to their normal operations as possible.
And like so can you talk about, again, there obviously average is a very difficult concept here, but how can we think about the volume of mineral feedstock that you are going to be importing annually or over whatever period of time to a typical deployment? Like, what are we talking about? Is that must be more than what they're using currently for dosing in most cases, or would it be equivalent? And then like, what is the net carbon removal you get out of that? Just so we can have a sense of like your average deployment, what would that deliver?
Yeah. So again, it totally depends on the facility size, right? But in certain instances, the goal is to completely replace the materials they already use, right? So it's equivalent in terms of the materials they already bring in for those facilities. And what we're targeting in terms of on a per facility site is thousands of tons of CO2 capture per facility, if not more. There's just a huge amount of carbon that's being produced because you're talking about massive amounts of water that are carbonaceous, right?
Yeah.
And so on a site-per-site basis for one specific deployment, because you have those elevated concentrations of water and CO2, which are key for enhanced weathering reactions, we can capture significant amount of carbon on a site-per-site basis, which is really what we're targeting.
And like for every ton of feedstock that you inject into the system, what is the net CDR?
Yeah, so it's similar to conventional enhanced weathering approaches, right? So it depends on the feeds, the stoichiometry and the chemistry of the feedstock. We have been able to test a wide range of feedstocks, and each of them have their own sort of capture ratio, if you will. We've been really focusing on initially carbonates, so limestone, and the idea behind that is several-fold. One, it's one of the most abundant rocks on Earth. Because it's very abundant, it means it can be sourced cheaply. There's basically limestone quarries almost everywhere. The reaction kinetics are rapid, much faster than silicate rocks. And then they're relatively clean, right? So they don't have carbonates. Oftentimes don't have metals that can get into the environment. And then the last one is people kind of know what limestone is, and so when we're engaging with operators, limestone is much more straightforward than something like funky sounding like wollastonite. So for limestone, it's about sort of 2.2, 2.3 tons of limestone per ton of CO2 captured, depending on the chemistry and the end member.
Got it. And then and does that, again, like, is that if they are managing pH, are you importing incrementally more mass into the facility to do carbon removal than you would without, like with their BAU, business as usual?
Yeah, so the goal is to match it. We don't want to, that is the goal. But then even when we're trying to achieve even greater impact, it might take more material to become on site. And one of the conversations we have with wastewater operators is exactly this. What does the mass balance of the system look like? And what's helpful is that, as I mentioned, these facilities are designed with access in mind, because there's a lot of material coming in and out. So there's material coming in through potentially septic tanks being delivered to the wastewater treatment facility. There's material going out as they're dealing with the solids load that has to be taken to a landfill or for agricultural application. So they're used to these kind of in and outs. And so it's not anything too shocking for them.
Got it. And just the question on the you're grinding the feedstock, is 500 microns still the particle size you're working with, or you're working with a smaller particle size, or does that vary?
Yeah, it will vary. It'll vary on a couple different factors. One of them is what's available nearby. We're trying to minimize the climate impact from additional grinding. One of the things that we've been focused on as we're engaging with quarries and mines near our deployment sites is being able to see if they have any waste material. So I know that's kind of the hot thing for a lot of people is identifying wastes. It turns out a lot of these quarries do have waste fines of limestone that don't necessarily have a use. And so we can actually source this material for pretty cheap. And the beauty is that not only is it cheap because it's a waste, but two, it's oftentimes very fine already. So it means that the connects can be very fast.
That 500 micron size is sort of like sand-ish. So you're not dealing with like tiny powdery particle size that could be hazardous to health.
Yeah, yeah. And I mean and in instances we have been identifying, see if we can get the finer grain material and making sure 100% we mitigate towards any sort of health impacts with fine particulates.
Yeah.
Part of Kevin's background thinking about engineered solutions, there is kind of a playbook with how to deal with fine grain materials from the mining industry. And so 100% integrating those approaches to make sure that we have minimal to no health or environmental impact is top of mind for us.
And am I understanding correctly from your presentation, and I guess also from the Frontier app, that the carbon removal is happening inside a closed system? And so you're able to measure the carbon removal inside a closed system. Is that correct?
Yeah, exactly.
And can you just like hit the high points of what you're measuring and how you're determining what the carbon removal is?
Yeah, I mean, I think this is, again, one of the beauties of tying into this existing infrastructure is that mass balance is just a little bit more straightforward, right? There's at these wastewater facilities, there's a discrete inlet pipe and a discrete outlet pipe. And of course, some of the facilities are open to the air. But generally, when you're thinking about the solids and the fluids, there's only one way for those places to go. And they already do a pretty amazing job of tracking that mass balance. So that makes our jobs even easier, right? We can make measurements both on the fluids of the chemistry, which is the main push of our sensor arrays, to quantify the carbonic acid system as it comes in. And then we can do the same measurements on the back end to quantify how much of that carbon we've now shuttled from sort of its harmful phase into its more inert phase. And then we can, if we want, we can even, over monitor by looking at various other aspects of the system, right? We can look at the solids to make sure that we're not losing any material to the solids phase that have gone unreacted. And those are all protocols that we have developed and allows us to do the MRV ourselves. But really, the goal is to make sure that this data, which is being collected, real time on site, can be provided to the facility or provided to anyone else who wants to take a look at the data and make sure that what we're doing is leading to practical CDR.
Got it. Okay, last question for me, and we have a lot of great audience questions, so Mega can come on and start hitting you with those. Your Frontier app talks about a risk of, I'm not sure if it's technically a reversal, but outgassing and or carbonate precipitation from your outflow. Can you talk about what that risk is and how you mitigate it? So like, is there a way that this can be reversed because you're either delivering, I guess it would be the wrong pH of outflow to the larger system, or because you're working with carbonates, they could precipitate? Like, can you just talk about like what that reversal risk is and how you can mitigate or eliminate it or mitigate it?
Yeah, absolutely. Yeah, it's one of the things that a lot of amazing folks on the academic side are working on right now. So there is, the idea is that there is a risk of inefficiency once you discharge your alkalinity to either river systems or directly to the ocean, right? That might, if you're adding extra alkalinity, you might get to a point where there's a certain amount of back reaction, where you have the reverse of the reaction that I showed on the slide that is actually leading to CO2 escaping. And so various folks are chasing this down right now. And there's some papers that are coming out. We are, because of our strong academic tie, we are part of a larger collaborative research network with folks at Texas A&M, for example, Professor Shuang Zhang, who is doing a lot of work actively looking at increased alkalinity discharge into river systems to quantify what that rate of potential leakage is and when does it happen. We wanted to make sure there's still more work that needs to be done from a scientific perspective. As we were putting together our package for Frontier, we wanted to make sure that risk was highlighted. And that's something that 100% needs more work, but there's some really smart minds behind it right now. On the ocean side, there's also folks at Yale and at Georgia Tech who are really working to estimate this process. And once we have a strong idea of like what that rate is and what are the key measurements we need to make, the goal is to fold this approach into our MRV and account for that with any of our operations.
Got it. And just to reiterate, your carbon removal is happening inside the closed system. You're removing biogenic elevated CO2 from the wastewater, and you're not relying on subsequent air seep gas exchange equilibration like OAE might. Just to be clear. Cool. This is fantastic. Thank you so much. And Mega, do you want to come on and do some audience questions?
Yes, we have quite a few. So yeah, just talking about the process itself first. How much do you have to sort of adapt what you're doing to the needs of the facility itself, and how much do they potentially need to adapt? Like, do they need to make changes to their sort of process to accommodate what you're doing, or is it like really seamless in all the different types of treatment facilities?
Yeah, that's a really good question. Kevin, I'll throw it over to you to take that one.
Yeah, I can take that. It's seamless. Let me put it that way, right? Basically, depending on how a facility might want to adopt a technology, whether it's as a straight into their mainstream process or as a side stream, it's essentially an add-on, right? And we're like, for example, existing pH alkalinity management systems will have, for example, a tank with a dosing pump. Our system is very similar, and so it's not anything new in that way. And depending on their goals as well, like if they're trying to maximize for carbon removal, right? How much we dose will change depending on those kinds of design criteria.
Okay, got it. It makes sense. And then just in terms of like, how long the process takes for sort of the minerals to be saturated, does that kind of align with the time that it takes to go through the treatment itself?
Yeah. So the wastewater treatment process, will have some amount of residence time as water is being treated, right? And so our whole design criteria is based off of that engineering and the chemical changes that are apparent in the wastewater. So we leverage the right amount of feedstock dosing at the right grain size, at the right rate, in order to maximize that CO2 removal, so that we're having weathering reactions happen, almost immediately. These fine grained carbonates are reacting very quickly. And so that's the beauty, again, is that we can make that measurement in this fully aqueous system, right? We're not talking about a soil profile, we're talking about a fully aqueous system, which makes it a little bit more straightforward to measure the impact that's happening, within minutes to hours.
Okay, got it. And how much is that affected by any other contaminants or things that might still be in the water that, that are still being processed out? Does that affect your minerals and your absorption, or is it really not relevant?
Yeah, that's a really good question. There's, a couple considerations to keep in mind. Settling is, a big component of wastewater treatment, right? And flock formation occurs. So one of the things that we have to make sure is that as we're dosing this material, it doesn't immediately all flock up, fall to the bottom of the tank, and then, get lost through the solids management system. That's something we want to keep an eye on. And actually, by adding limestone and having that limestone dissolve, it's actually beneficial to flock formation, which wastewater facility operators really like. That helps remove material. But we really want to make sure that we're not also then just removing unreacted rock. That being said, even if it settles out as it's part of the sludge water interface, that sludge will oftentimes have even longer residence time, and have more opportunity for that rock to react with carbonic acid in that environment.
Yeah, okay, makes sense. And then just in terms of like servicing, maintenance, that kind of stuff, are you at a point yet where you're encountering those kinds of issues, and what does that look like?
Yeah, I mean, I think with everyone's first system, there's always downtime as you learn to troubleshoot different aspects, sensors, pumps, filters. We've definitely run into those at first. And there's a lot of learnings that we've built out during our time at Yale with the Earth and Planetary Sciences Department and the Carbon Containment Lab to learn those aspects. And now, there's the beauty of engineered solutions is there's oftentimes, straightforward solutions to them, which we've now folded in. But I think one of the key things is making sure that our process continues to operate, continuously. This is a continuously operating process, and matching our ability to deploy into the wastewater treatment process in a way that doesn't screw with their first goal, which is to treat wastewater, but does it in a way that is also making a positive impact through CDR.
Got it. Okay. And then just thinking about CDR impact, we had a couple of people ask how do you think about classing this, I guess, as a removal rather than a reduction, because it is sort of happening at a point source and you take advantage of this concentrated stream. Yeah, how do you think about that question?
Yeah. Yeah, that's a really good one. I think one of the best ways to kind of wrap our heads around this is kind of the equivalent to bikers or BECs. So you're basically taking advantage of biomass fixing carbon, and then biomass rapidly converting that solid carbon back into CO2. And if you really track the carbon cycle, we're basically taking atmospheric CO2 into biomass, and then before it goes back into the atmosphere, shuttling it into the long carbon cycle.
Right. Okay. Yeah, makes sense.
Yeah.
And I know you might have mentioned some numbers, but do you have a sense of the total like megaton, gigaton scale potential if you were to deploy this, worldwide or in a particular area that you're looking at?
Yeah. So we've been thinking about this globally, but really focused on our impact in the US. It's obviously where we're mostly based at the moment. So I've done a lot of mapping, thinking about who are the municipal and who are the industrial facilities that we could potentially partner with, and then sizing from that. And a lot of that sizing comes from the empirical results that we already have from our initial experiments and initial field trials, and then scaling that up. And so just in the US, the scale that we're talking about in terms of actual CDR, the total potential, right, is on the scale of hundreds of millions of tons of CO2 per year.
Okay.
I think really puts it up there amongst other nature-based solutions. So yeah.
Yeah, cool. I mean, we did have that is a lot and is very substantial already. We had a couple of people ask like if there are other sort of similar processes that this could plug into. Someone asked about like microbial digestion of plastics. Does it make sense, either engineering wise or chemistry wise, that this kind of would be applied elsewhere, or is it pretty particular to wastewater treatment?
Yeah, I think there's ways that this can be applied elsewhere. I think even outside of one of the things hopefully we made clear is that even outside of just pure CDR, there's also knock-on effects that make, that can have effects on the wastewater treatment process itself. So by adjusting the pH of the wastewater, we can make things like microbial nitrification happen more effectively. And that when that happens more effectively, you have less nitrous oxide emissions. And so in some of our field trials, we've seen a decrease as we do this pH adjustment. We see a decrease in nitrous oxide emissions. That's something that is top of mind of the thing that we want to really pursue next. Right now, we're focused on CO2, but something I think for us, there's a lot of interest there. But I think even for the broader wastewater community, following up on dealing with nitrous oxide emissions is really important for folks. So if we can do 2 in 1, I think that could be really exciting and really quite transformative. Kevin, is there anything you wanted to add about sort of other approaches or how this could be used elsewhere?
Sorry, I was answering a Q&A question. What was the question?
Yeah. Just in terms of like other ways this process could be applied outside of wastewater treatment, other similar processes that it could plug into potentially.
Oh yeah, no, okay. So yeah, basically what Joe said, like plenty of other use cases. Because enhanced weathering is flexible, right? Especially if you're doing containerized systems, it can be engineered and deployed in places where we see opportunities for carbon-rich water, essentially.
Got it. Okay. Just a couple more before we go, I think. How do you prevent the carbonates from like settling out or turning into kind of a lime scaly issue on the equipment? Is that a problem that you run into?
Yeah, Kevin, do you want to take this one?
Okay. Repeat the question, please.
Oh yeah, just how do you kind of prevent the carbonates from settling and like forming sort of scales on the walls and equipment and things?
Yeah, so that's a good question. So one, designing to make sure where you're dosing is important, right? And so where in the treatment step, like for example, if you're going to do it in aeration tanks, right, where it's well mixed, right? So that'll help mitigate the impacts on it scaling. Understanding also if there are other treatment processes that might have effects downstream, and also controlling and making sure that the pH that environments that you're putting it in is amenable to stay dissolved as trapped carbon. So yes, there's a lot of different levers and controls to worry about, but it's not there's not anything that has already been done. And with our geochemical expertise, we're able to identify and prevent those kinds of formations. Yeah.
Cool. And then one last one before we go, maybe a bit of a big question given that you have 3 minutes, but can you just talk a bit about how the energetics and economics compare to other forms of CDR? Particularly someone asked about DAC, but yeah, whatever you might want to chat about in that.
Yeah. So I think one of the nice things again about tying into existing infrastructure is that that makes the sort of CapEx and OpEx burden for us a lot lighter, right? We can take advantage of the fact that society has spent, trillions of dollars of infrastructure building these bioreactors, building the pumping infrastructure to do this process on its own. And so by basically tapping into that makes it a lot lighter for us. And as Kevin mentioned, one of the things that we're targeting very seriously is being able to generate a carbon credit that's less than $100 a ton. And when you look at the breakdown in sort of our future systems that we predicted of what are the major drivers of the cost, energy is quite low. As you can imagine, the most of the energy is taken up in any sort of rock grinding and like operation of the system. So that's operation of the agitators for the dosing tanks, the sensors themselves. That's pretty minimal. And what's really the big driver of cost for us is the cost of the feedstock. Like a lot of enhanced weathering, that is, you're basically using a natural sorbent that is being consumed during your process, right? So on a ton per ton basis, you're having to use a lot of this material to keep your process running. So the sort of the major drivers for us is not necessarily the energetics, but it's actually the cost of the feedstock.
Cool. I think that's all we have time for. I know we had a lot of questions this time, so sorry if I didn't get to yours. And Toby, whenever you are ready, I think we have some things coming up.
Yes, that was great. Thank you, Mega. And thank you to the audience for such great questions. And sorry we didn't get to them all. And Kevin and Joe, that was really fantastic. So thank you for being with us and for such a great presentation. Good luck with your next deployments. So much that we didn't get to, but maybe we'll have to have a follow-up session to cover your work with Ebb, for example. We put a link in the chat about that.
Amazing. Absolutely. Yeah. Thank you for having us again. Really excited to chat with you guys and look forward to the next one.
Yep. Take care. A few programming notes from us before we close. Sorry for my slow computer. So next week, we have a special Thursday event with our friend Sebastian Manhart, who is a policy advisor at Carbon Future. He was on a few months ago. Mega did a great session with him. We're going to have him back on because there's so much going on right now with European carbon removal policy that's really super, super important for the future of carbon removal, I would say, without exaggeration. So please join us for that. Again, next Thursday, 11 a.m. Eastern. On This is CDR Tuesday, we're super excited to have Matt Long from Seaworthy, which is a new focused research organization dedicated to advancing high quality MRV for marine CDR. And that's going to be a really great and topical discussion. On the 12th of September, we have our friend Philip Moss, who runs carbon removal for NextGen and South Pole. And I think that one's going to be really interesting as well. We're going to take, we think, the week of the 19th off, although stay tuned for a possible This is CDR Live. So we think we're off on the 19th. And then on the 26th, we have Eva Tom, who is an expert on supranational governance, and she's going to tell us what's going on now with the Article 6 discussions, which are, again, super important for the future of carbon removal, and the timing will be such that she'll be coming on for us in advance of a possibly really important open period for comment on that. So please join all of those. Chris put a link in the chat to a page where they all are, and you can register. Again, next week, Dr. Matt Long, super excited for that. We thank you all for being with us, and we will see you. Have a great long weekend, holiday weekend in the US, and we'll see you next week. Bye.